we will talk about resonance today. They are delocalized pi MOs. Before starting resonance, we will see first a few reactions. This is ethylene. This is olefinic bond. It is a well known reaction. When this reacts with bromine, say in CCl4 solvent, you get this is addition reaction, very well known reaction. But if you take butadiene, which we may write it as this is actually known as butadiene 1,3, and you add bromine to it in the same medium, the product expected is 1 mole of bromine and 1 mole of butadiene. You will expect this as the product. Two bromine atoms attached here or here, the same thing. But actually, this is not the only product that is formed here. You also get this is 1,4 addition, this is 1,2 addition, here 1,4 addition. This is quite unexpected. A double bond is here. In the original compound, there was no double bond here. The quantities of these two products differ slightly with the solvent and temperature. At minus 35 degree temperature, minus 15 degree centigrade, this amount is nearly 48%. The proportions vary with temperature and solvent. So, this has to be explained why these two products are formed. This is usual product, this is abnormal product. This has to be explained, and here we will take help of resonance. If you take benzene, which has been shown to have 3 double bonds, this or at other alternate positions. If you treat this with bromine and CCl4, no reaction. This is not explained. 3 double bond and saturation, yet no addition reaction. So, let us see what happens with these double bonds here and here. We will call this double bond as localized double bond. If you take the case of pentadiene, here if you treat this with bromine, you get the expected addition product. So, no problem here. So, there is something with the alternate positions of the double bond. Here they are not alternate, you get the usual product. This is pure olefinic bond, this is pure olefinic bond, this is pure olefinic bond. These are probably not olefinic in nature. Let us see how this type of thing develops. If you take the case of butadiene and form the molecular orbital picture of this, all are sp2 hybridized, one p orbital here, one p orbital here. There are 4 p orbitals standing perpendicularly on this plane of 4 carbon atoms. Now, an overlap of p orbitals will take place because they are parallel to each other, these two are parallel to each other, and one possibility is that these 2p and these 2p overlap, which can be represented by this valence bond structure. This is molecular orbital picture, this is valence bond structure. Another possibility is that this can overlap with this, forming a double bond between C2 and C2 and C3, these p orbitals remaining unused. We can write this structure as this: a p orbital standing here, one p orbital standing here, there is one electron here, one electron here. Other possibility may be these two electrons coming here, no electron in this, or this structure negative charge. So, which of these is the correct structure? None of these is the structure representing the molecule in toto. So, here now we will say that neither this nor this singly takes place, but actually this also overlaps with this, the total overlap of these 4 p orbitals, and this is the real picture of the molecule, which we cannot represent by a single structure, single valence bond structure, and we put a double headed arrow in between these structures and say that butadiene molecule is the hybrid of all these structures, none of them completely individually representing the molecule. The actual molecule is the resonance hybrid of all these valence bond structures. So, this phenomena is known as resonance. In benzene, similarly, butadiene, you can see I have shown this molecule here. If these 2p overlaps, these 2p overlaps, this structure. but if you leave it aside and overlap these 2p, you get these type of structures. In case of benzene, as we had seen in the last video, there are 6 p orbitals standing perpendicularly. These are hydrogen atoms. These are hydrogen atoms. One possibility is that these two can overlap, these two and these two, forming this valence bond structure. Another possibility is that these two can overlap, these two can overlap, and these two can overlap. So, we will say that none of these is a complete picture, but actually see this benzene molecule, p bar is standing, all these p standing parallel to each other, and each orbital has 2 p orbitals parallel to it. So, this overlaps on both sides, this on both sides, and a total overlap takes place, and this forms delocalized pi bonds. Such type of pi bonds are called delocalized, and we put a double headed arrow between the two and say that benzene is actually a resonance hybrid of these two valence bond structures. So, the result is, you can remember, if 3 or more than 3 p orbitals stand parallel to each other on adjacent coplanar atoms, then this type of delocalization will take place. At least 3 p must be there, 4, 5 and 6 may be there, at least 3. Parallel p orbitals on adjacent sigma bonded coplanar atoms, then this type of delocalization will take place. In the next video, we will see many more examples and to know how to write resonating structures and the consequence of resonance in the molecule. Okay.